Hello and welcome to Lecture 17. This is our first lecture on the topic of optics, talking all about the things that light can do. One of the first things we're going to focus on is how light can interfere in what's called a double slit interference pattern, which is really just two sources of light, which are waves, combining at a single point. We're going to learn that the index of refraction is a value that relates to the effective speed of light in a transparent material other than a vacuum. This is kind of a standalone idea that was going to be loosely related to the rest of the examples in this section, but it is important to introduce it now. We also want to recall what happens when two waves coexist in the same place at the same time and how this leads to constructive and destructive interference. I say recall because this is the same phenomenon that would happen with sound waves or even waves on a string, such as in a standing wave in a stringed instrument. We also want to learn how to understand the interference pattern formed by the interference of two light waves, the pattern that would show up on a screen, which is going to be the case in many of our examples. Okay, so let's take a look at our key terms. The first one is the index of refraction, that standalone idea I mentioned. It is the ratio of the speed of light to velocity. Now you might say, wait, velocity of light, isn't that just the speed? Well, yes, in a vacuum, but light doesn't effectively travel at the same speed when it passes to it through a transparent material. The index of refraction is also a dimensionless number that describes that material because the different materials cause different speeds of light when the light passes through them, and thus it is a material-specific constant, okay? It's determined empirically or with experiments. For example, the index of refraction for glass is 1.4 because the light wave velocity in glass is c, the speed of light in the vacuum, divided by that value of 1.4. So in other words, it's 1.4 times slower, okay? We divide by 1.4, okay? All right, so that's the index of refraction. Now on to the main concept about interference, which is the superposition of waves, okay? So an interference pattern is a pattern of bright and dark bands, which are often called fringes, that represent locations of wave constructive and destructive interference, okay? Constructive or destructive. Specifically, a double slit interference is the effect of wave diffraction from two-point light sources. So two light sources that then have waves that spread out in all directions. Let's zoom in on this example image. So here are two slits. They're openings in some wall, but they're functioning like two new sources of waves because we can see these waves spreading out from that source, that effective source. The waves spread out because that's what waves do. That is called diffraction. It is a principle or a quantity of all waves. As these two wave sources spread out, they begin to overlap, which we can see starting here. When those overlapping waves arrive on a screen, they will create bands of dark and bright because of that combination of constructive and destructive interference. So in other words, when the waves are in phase, when crests or peaks overlap with other peaks, you get a bright spot. On the other hand, when the waves are exactly out of phase and a crest overlaps with a trough of the other wave, then you get cancellation and you get a dark spot. That is the underlying principle about everything we're talking about in this lecture, okay? All right, so that is an interference pattern. The light that we're looking at, the light that comes in and makes these patterns, is coherent light. What that is light that is in phase initially, all right? So it's only the differences in path lengths that are causing the light to arrive out of phase, and it's all going to have the same wavelength or same color, all right? And examples assume coherent light, okay? Now let's talk about the approximations that are made in this content because they're very much front and center, these approximations. The first one is the parallel ray approximation. It is a helpful, I'm going to zoom out a bit, a helpful simplification that says, since distance from the slits to screen is so much greater than the slit spacing, in other words, R is much, much greater than D, that means that the path length difference is approximately equal to D sine theta. What do I mean by that? Well, take a look at these two images up here. So here are the quantities I'm referring to. D is the distance between the two slits, those two effective sources of light. The distance from the slits to the screen is R. Okay, that's a long distance. Okay, Y, by the way, is going to be the distance from the central bright spot to whatever order bright spot we're talking about. But we'll return to the idea in just a minute. But the idea is if this r is very long, then we can assume that the rays, that's these blue lines, are effectively parallel. Therefore, if we subtract one ray from the other, so that's our idea of R2 minus R1, then what's left over is just this segment here, d sine theta. See, distance between the slits and a right triangle with this angle. All right, because again, I just took R1, imagine taking it over here and subtracting it from R2, just kind of cutting off everything that R1 cancels out, okay? So that is a true statement if we assume the rays are parallel. Now, in reality, they're never quite parallel, and because then what happens is we can't take R1 and exactly subtract it. Imagine taking this actual distance R1 and kind of taking it over here, we'd have to twist it a bit, and it would be longer, see? When we subtracted it, it would actually be, what would be left over would be less than d sine theta. So R2 minus R1 would actually be less than d sine theta, and they're not equal, okay? Now, this is fine, we can do this geometry, but it's actually quite cumbersome. And so it's very helpful to always make this the parallel ray approximation, and we will in every example in this lecture. Now, there's another approximation that we make sometimes, because sometimes it's justified, and that's the small angle approximation. Okay, it can be sometimes used, again, when the distance from the slits to the screen is much, much greater than the slit spacing, since that means that the right triangle formed with theta, the theta we were just talking about, is such that the hypotenuse is essentially the same as the length of the longer side. Because you think about this triangle, if it becomes such a long triangle, then this long leg of the triangle is so much longer than this short leg of the triangle that this long leg is effectively the same length as the hypotenuse, all right? Now that only works for very long, narrow triangles, all right? And in that case, tangent theta, opposite over adjacent, is basically the same as opposite over hypotenuse, since adjacent and hypotenuse are the same, all right? So that allows us to, this becomes a true statement since this becomes approximately the same, okay? Now, again, that was approximation we'll use sometimes, and you'll see when. So let's get on to our key formulas, all right? So first of all, we have two kind of basic ideas that are based on the parallel ray approximation, but that's all. In other words, these two formulas do not use the small angle approximation. What do they tell us? Well, let's look at the variables first. D is the distance between the slits, just like labeled in the figure, measured in meters. M is the order of the fringe, okay? It's a dimensionless integer. It can be 0 at the central bright spot, that'd be this bright spot right here in this figure up above, all right? Because there, the path length difference is 0, so the waves must arrive in phase, all right? So that's an M of 0. Or as we move away from that central spot, then we have like an M of 1, an M of 2, and so on, okay? See my writing up here, okay? So that's the idea. It's just counting where we are in terms of our pattern, okay? We also have the angle. This is the angle formed by the right triangle with Y bright and R, all right? Because this formula up here is for bright spots, this formula is for dark spots, okay? Y bright is the distance from the central bright spot to whatever order bright spot we're talking about. You can see Y used in this figure. In other words, its distance is measured along the screen where the pattern is visible. And lastly, we have the wavelength lambda measured in meters. That's the actual wavelength of the light. If it's visible light, it's going to be on the order of hundreds of nanometers, maybe something around 500 nanometers. But we can also have other types of light like infrared or ultraviolet or anything. Okay, so I have a couple of images here that illustrate the ideas of constructive and destructive interference, right? Based on this equation. Right here we have an example of two waves arriving in phase. Notice, I'm gonna zoom in on this a bit. Wave 1, the orange one, has a length R1 that's exactly equal to 4 wavelengths. All right. Now the wavelength is shared. They're not actually two different colored waves or anything. I just labeled them different colors to make them clear, but it's all the same light because it's coherent light after all. But anyway, R2, this length or this distance from slit 2 to the point we care about, well, that distance is exactly 5 wavelengths long. Well, that means that when the waves arrive, they arrive in phase and we get a bright spot. So that means that this angle would be an angle that corresponds to a bright spot, okay? Now, the order of the bright spot would depend on a lot of factors, right? We don't know exactly which one it is, okay? Well, I guess we do know because it's a wavelength difference of 1 wavelength, so it'd be M equals 1. So it's the neighboring bright spot to the central bright spot. So the pattern, we'd have a bright spot right here that represents high intensity, and there would be the second one, okay? And again, that's because exactly 1 wavelength difference, okay? Now, we could also consider the cancellation formula, which is represented down here as the second one. Here's an example where we have slits. They're closer together now, and that has changed the effect and made it so that R1 still is exactly equal to 4 wavelengths, but now R2, instead of being equal to 5, is only equal to 4.5. That means when the waves arrive, they arrive exactly 1/2 wavelength out of phase, and they cancel out, and we get a dark fringe. So the distance from the center to our location now is Y dark, and that means that our angle is an angle that corresponds to a dark spot. Specifically, the first dark spot. That would be the kind of that first dark spot on the edge of the central bright spot. Okay. Now we got a couple more formulas. Let's take a look at those. This first one here is none other than the small angle approximation. All right, so check out what happens. So when the angle, that's the angle of the triangle, is less than or equal to about 15 degrees, now that's, again, it's approximations, that's a general rule, then, as I said before, tangent theta approximately equals sine theta, because the hypotenuse is about the same length as the length of the longer leg of the triangle. Okay, and the bright fringe formula can be rewritten as d tangent theta equals m lambda as just this. Why is that? Well, because tangent theta becomes opposite over adjacent, okay? And there we go. We just rewrote it. All right, well, tangent theta always was opposite over adjacent. The whole thing I did was just substitute sine theta with tangent theta. Okay, just recall the formula on the previous page. So now we have this nice expression that has no trig function in it. So this can be an easier way to work with our equations. We don't have to do any inverse sine functions, for example, to solve for our angle. It is just simply easier to work with. Is it dramatically easier? No, but it is nominally easier. So if we can use it, we will go ahead and do so. All right, in this case, r, which we've talked about before, but it hasn't shown up in our formulas, is the distance m from the slits to the screen. Now, the reason r didn't show up in another formula is not because we can't solve for r without the small angle approximation. It just would have been a separate step. All right, here it's all as one. Okay. And then y is the distance along the screen, is the distance in meters on the screen from the central bright fringe to the nth, it's a mouthful, the nth order bright fringe. Okay, so like first, second, third, and so on. Because the central one is the 0th order. It's the 0 point. Okay? And then finally, right, we mentioned this is our first key term, but as our last equation, the index of refraction, just represented by the number n, or the letter n, excuse me. And it's a ratio of the speed of light over the velocity. So speed of light over the velocity. So it's always greater than 1. Okay? The index of refraction, always greater than 1. All right, so let's look at our examples. All right, so we got 3 types of examples. I broke them into some categories here. Type 1, problems that involve the locations of interference maxima or minima using the small angle and parallel ray approximations, okay? So again, that's gonna be all about using this equation here, okay? Type 2, problems that involve location of interference maxima or minima using only the parallel ray approximation, all right? May compare accuracy of approximation methods, all right? Now, see, that's gonna use the 2 formulas on the previous page. Finally, type 3, problems that involve locations of interference maxima or minima when the light travels through a material with a refractive index other than 1, because n equals 1 in the vacuum, because in that case it would just be c over c, right, which is just 1. Okay, let's take a look at our first example. A source of coherent light with a wavelength of lambda equals 680 nanometers passes through 2 narrow slits with a separation of 150 microns, or micrometers. A screen is located 2.2 meters directly behind these slits. Using the small angle approximation, right, and again, I would state that on the problem, but here, color-coded wise, that it's going to be a small angle approximation problem. How far is the 4th maxima from the central maximum? How far is the 6th minimum from the 3rd maximum? So we got a distance between minimums and maximums. If the screen is 30 centimeters wide, then how many maxima will fit? How many will be visible? All right, so here's a picture, get things started, right? Oh, excuse me there. Here are the slits, right? S1 and S2, distance between them, little d. All right, the distance from the slits to the screen, r, okay? There's our central maxima with our m of 0. And we're interested in the 4th one, right? So that n2, 3, 4, so over here. So this is the distance along the screen is y m equals 4. All right, you could call it y4, all right? So here, m equals 4. So that means we're gonna write this formula with 4 in it, okay? So the distance for the 4th one is simply plugging in our screen distance to the screen, our 2.2 meters. We'll plug in our wavelength of light, again, 4th order, and then our separation distance. So very much plug and chug, and we find that that distance from the center of the central maximum to the center of the 4th maximum is 5.21 centimeters. Okay, very good. Now, in part B, we're asked how far is the 6th minimum from the 3rd maximum? Okay, so how do we do that? Well, the distance between any 2 maxima is. Now, this is gonna be really helpful because often we care about not, always measuring from the same fixed point instead of measuring between points? Well, let's see. So in that case, I want a delta y. That would be the distance between consecutive maxima. Like maybe, this would be an example of delta y, okay? Well, it's ym plus 1 minus ym, all right? So if we plug in m plus 1 for m and then plug in just m for the other, then we end up with this expression here, okay? Well, then I can then distribute my r, and I get these two terms that cancel out, see? Because I would have cancellation of terms. So all that's left is this. Aha, so the distance between any two maxima is just r lambda over d. Oh, that's a helpful formula. So the distance between the sixth minimum and the third maximum can be thought of with this little picture here. Here I've just drawn more of them without the rest of the dimensions shown. So we got our central one, or our 0th order, all the way up to m equals 6 over here, right? Okay, and they get decreasing in magnitude for reasons of increased distance and the idea that intensity falls off with the square of distance. Okay, and so then if we want to go from the third maxima to the minimum right after the sixth minimum, because it's 1, 2, 3, 4, 5, 6, all right, then we'd have 3.5 as our delta y. Okay, so 3.5 delta y, right? Because all the minimums are exactly halfways between maximums. They have to be. It's all symmetrically distributed. So then it would be 3.5 times this, or 3.5 r lambda over d. Okay, so plug in our values, and we get 4.56 centimeters. Very good. All right, so finally in part C, we want to find how many fit. So the number of bright fringes that fit on a screen is equal to the length of the screen divided by delta y, and then add 1. Why 1? Well, because for every delta y gap, there are 2 bright fringes, right? Because think about it, a gap is the distance between the fringes, but now you counted 2 fringes. So, if you have a gap that is, that includes 2 of them, well, now there's 3 bright spots, right? So it's always 1 more than the distance you have, okay? And we always round down to only count complete bright fringes, okay? So in that case, the number of complete bright fringes that fit would just be L over delta y plus 1. All right, well, we know the form of delta y because we know it up here. So if we're dividing by it, I would just take the reciprocal of this. So then I get LD over r lambda plus 1. And then it's just a matter of plugging in our quantities, and we find out that 24 bright spots will fit fully on a screen that is exactly 30 centimeters wide. All right, and again, it depends how far away the screen is, but that came up in our formula. Okay, let's move on to our next example, example 2. In a young double-slit experiment, coherent light of wavelength 580 nanometers illuminates 2 slits that are separated by 212 microns. Okay, again, micrometers we call microns. Using the small angle approximation, what is the separation between adjacent bright fringes on a screen, 88.9 centimeters away, and what is the separation between adjacent dark and bright fringes? All right, so just reiterating that idea that we can find separation between them because it's such an important concept. So the separation between adjacent fringes we already know is just r lambda over d. So it's just a matter of plug it and chug it, and we get 2.13 millimeters. Now the separation distance between adjacent dark and bright fringes would be half of that. So it's 1/2 of delta y, or 1/2 of 2.13 millimeters, which is 1.07 millimeters, right, for these numbers. All right, so right on to example 3. Let's do away with the small angle approximation and use just the parallel ray approximation. So infrared light is shined onto 2 slits with a separation distance of 518 microns. The third maximum of interference is located 21 degrees, measured from the midline of the slits. What must be the wavelength of the light? If this maximum was visible on a screen located 50 centimeters from the slits, how large would the screen need to be? And using the same screen, if the light was replaced with the red light with a wavelength of 709 nanometers, then what would be the highest order maximum to fit? Okay, so here we're going to start with the formula that doesn't use the small angle approximation, all right, and that we're going to solve for lambda, okay? And we do that, and then we get 6.19 times 10 to the negative 5 meters, okay? So much longer than the wavelengths for visible light because it is, after all, infrared. Infrared can be, up to fractions of a millimeter long, okay? Now in part B, let's then take that information and consider that, yes, this absolutely applied to the idea of, based on that angle, finding the location, right, for that particular order maximum, all right? In this case, the third order maximum. But then that also applies to physical distances, with the distance of a screen and the actual distance along that screen to the third order maximum, m equals 3, all right? So that's what this triangle represents, so those physical distances. And we're going to go ahead and solve for y3, all right? So I go ahead and solve for y3. It's just r tangent of theta, taking the value that we were given, right, and the distance to the screen, and we get that it's 19.2 centimeters. Okay, now that means the screen has to be twice that long because it has to be able to fit symmetric bright fringes on either side. So the overall screen would be 38.4 centimeters wide. Okay, now finally part C. Using the same screen, how many would fit if we replace the infrared light with red light? Still long as far as visible light goes, but much shorter than the infrared light. Okay, well now, we set our angle, and this is m for the mth order, to 21 degrees, okay? And then we're gonna solve for m with this new wavelength. Okay, so we set up the formula like this and just go ahead and solve for m. And we end up having 261 as our order. Oh, wow, that means we can fit 261 in here? That sure is a lot, but it is, like 100 times shorter, so that kind of makes sense, okay? So we fit a lot of bright spots with this visible red light, okay? Now let's think about this. So, and that's from rounding down because it was 261 point something. Now, with precisely the angle that corresponds to 261, let's find out where that bright fringe is located, how close to the edge, all right? This wasn't asked for, but I thought it'd be interesting. So if we go ahead and do that, we can then plug back into the inverse sine function and find that it's at 20.9, okay? So right close to all the way to the 21 degrees of angular displacement. And so then we can then plug that into a distance and find out that it'll be right at 19.1 centimeters. So right on the edge of our screen, okay? Okay, all right, so let's move on to our next example, example 4. All right, so in a Young's double slit experiment, bright coherent light with a wavelength of 617 nanometers illuminates two slits that are separated by 65 microns, right? So very, very small separation. You notice the other ones are tended to be hundreds of microns. This is only 65 microns. A screen is placed 21.3 centimeters away from the slits. Using the parallel ray approximation and the small angle approximation, what is the distance on the screen between the 20th bright fringe and the central bright fringe? All right, and then what is the percent error between the distance you found in part A and the distance found not using the small angle approximation? Okay, that's why this is a blue problem, because we're going to both do it with and without the small angle approximation. All right, so using both approximations, we simply plug in and we find out the distance is 4.04 centimeters. Distance from the central bright spot to this 20th order bright spot. Okay, now without using the small angle approximation, it's a little bit more work. We got to go ahead and find the angle. All right, so we're going to set this up. All right, solve for the angle using inverse sine. All right, plug in the numbers, and we get 10.9 degrees. Then, all right, this, by the way, is small enough that using the small angle approximation was reasonable, but it's kind of pushing up close to 15 degrees, so there will be some error, right? So how much? Well, let's see. All right, thus the corrected maximum would be using this angle, plugging it in with our known distance to the screen, we find out that the distance is 4.12 centimeters. So this is where the bright fringe is actually located. This is where we thought it was located with the small angle approximation. So you see they don't actually exactly match up, okay? So to get a percent error, we're going to take our corrected distance minus the original approximate distance divided by the corrected distance times 100. All right, plug in our numbers, and we get 1.82%. So less than 2% error, which is why it makes sense to use the approximation, okay? But again, you don't have to, right, if you want to get under 2% error. Okay, let's do another one. But this one, instead of with infrared light or visible light, with radio waves, or very long waves. Now I changed the number here to make the problem work a little bit better. I'm going to have my two radio antennas 150 meters apart. They are on a north-south axis on high mountaintops. On the seacoast, the antennas broadcast identical AM signals, right? So coherent light, in phase at a frequency of 5.9 megahertz. We'll have to turn that into a wavelength. A freight ship 71 kilometers offshore travels towards the north at 15 kilometers per hour and passes east of the antennas. A radio on board the ship is tuned to the broadcast frequency. The reception of the radio signal on the ship is maximum at a given instant. How much later until the next occurrence of maximum? So all we're going to do here is find the distance between maxima and then just use this ship idea to find the time it takes to travel that distance. And the ship is traveling at a steady rate, so it should be easy. Okay, leaves that part. So here's the picture, right? So essentially we have two slits, so two sources, okay? There are some distance apart, okay? Here's the distance between maxima, okay? Here's our ship moving at velocity v, and there's our distance from the slits, or the sources, to the screen effectively, the screen being the path of the ship, okay? All right, so we need, as I said, to turn that frequency into a wavelength, just using this relationship between the speed of light, wavelength, and frequency, and we find that it's 50.8 meters long. Okay, now let's move on to the bulk of the problem. We cannot use the small angle approximation here. So instead, we're going to use this formula, okay? And with m equals 1, since we are looking for adjacent maxima, okay? And we're going to go ahead and find this angle theta. Okay, that ends up being 19.8 degrees. So indeed, our choice of not using the small angle approximation was justified because that's well bigger than 15 degrees. Okay, And then we're going to go ahead and solve for delta y by taking an angle and plugging in the tangent theta. And the whole reason we have to do that, again, is because here tangent theta does not approximately equal sine theta. So we have to treat them as separate sine functions or separate trig functions. Okay, so then we go ahead and solve for that delta y. And there's our value, 25.6 kilometers. So then it's simply a matter of saying, well, the velocity of the ship is just delta y over time. And that means the time is just going to be that distance of 25.6 kilometers, that delta y, divided by how fast it moves at 15 kilometers per hour. I left everything in kilometers so they'd cancel. And our answer is going to be conveniently in hours, 1.71 hours. Okay, that's a long time to have bad reception. But of course, this could be better designed by not having the antennas so close together. If we just make D bigger, then we can get to a point where the small angle approximation quickly become valid. So point is, don't put the antennas so close together. Okay, and indeed, that's the idea. If D is really small, then you often get into situations where you cannot use a small angle approximation, and you're left with very large gaps between bright spots. Okay, all right. All right, quick concept question, because I just want to remind us that we always use the parallel ray approximation. All right, so the question, after light from a source passes through two slits, a first order bright spot is seen on the wall at point P. Which distance is equal to the wavelength of the light? Make sure you can answer this. Which one's equal to the wavelength of the light? It's A, right? Because A is the path length difference, which is exactly m lambda. And here that's just lambda because m is 1, because it's the first bright spot. And that's only true because of the parallel ray approximation, because we're assuming that we can just subtract this length from this length to get this little difference in here, okay? All right, final example, the one that involves the index of refraction. Light with a wavelength of 450 nanometers is shown through a double slit with a spacing of 390 microns that is attached to a long side of a tank, because the tank's going to hold a liquid, that is 1.24 meters long. The tank has a width of 26 centimeters and has a screen that runs the width, okay? Okay, a clear liquid is poured into the tank with an index of refraction of 1.73. All right, then how many bright fringes will become visible on the screen as compared to when the tank was filled with air? All right, so based on the dimensions of the tank, we can check for an angle small enough to support the small angle approximation. So let's see. All right, so here's going to be their check here. I have width and length, so W and L. All right, and I just want to then 26 centimeters, 124 centimeters. So, and here's the picture. There's the length, there's the width, there's the separation between the slits. All right, so it ends up being 5.98 degrees. So yeah, it checks out. We can use a small angle approximation. All right, so the number of bright fringes that fit along the width before the liquid is poured in, okay, is just simply n max. So it's going to be the width over delta y plus 1. This is similar to the previous example. And let's see what we get, right? Plug in our numbers, and we find that 182 fit. Okay, so what happens though when we pour in the liquid with our index of refraction? Right? When the liquid is introduced, now we have a reduced speed for the wave. And that means that the wavelength is going to change. We have a new wavelength that I'm going to call lambda prime. So lambda prime is the new wavelength. And notice the frequency is unchanged. That's absolutely true of waves. When they slow down, the frequency doesn't change, just their wavelength. Thus, the relationship between the original wavelength lambda and the new wavelength lambda prime comes from the following. All right, so we get to take c over n. I've just replaced velocity here. I'm just setting velocity equal to velocity. All right, and then I have lambda prime times f, and then I'm going to replace c with lambda times f, because that's the original wavelength. Cancel out the frequency, because that was unchanged. And there we go. We find that the new wavelength is the original wavelength divided by the index of refraction. This is, again, a very helpful formula talking about the effect of index of refraction on wavelength. Okay, so now we just find out how many bright fringes fit with this new wavelength, lambda prime. All right, replace lambda prime with n over lambda. Sorry for two n's. Here, this is the number of bright fringes. This n is the index of refraction. All right, plug in all our values, including our index of refraction, and we find out 315 fit. So that means that we have a difference of 315 minus 182, or we ended up with an extra 133 bright fringes due to pouring the liquid in there. Pretty cool. All right. And then what would need be the refractive index in order for 250 to fit? Well, it's going to have to be something less than 1.73, because we know that allowed 315 to fit. So in this case, we just set n max equal to 250. So set it up like this. In this case, we're solving for n, not n max, n. And remember, n represents the index of refraction. And plug in our values, 1.37. Indeed, less than 1.73, just like we'd expect. Okay, well, I hope this lecture has been interesting and informative. Thank you so much for watching.